All right, ladies and gentlemen, here we go again. Concentration. How the concentration affects reaction rates. We'll pick a pen color, and here we go. So let's look how the rate constant affects rate. So that's the first thing we need to do before we look at anything else. So any kinetic experiment, we'll look at either formation of a compound, which is going to be positive rate, or the reduction of a compound, which is negative rate. And the rate is basically the change in concentration over the change in time. So we're looking at degradation of hydrogen peroxide to hydrogen and water. So what we have is H2O2, and we're going to go to H2O, and actually it's going to produce O2. And let's see, make sure I get the coefficients. Two of these, one of these, and two of these. And so the rate of, comparatively to all these, is that the rate of oxygen being produced is 1/2 the rate of water being produced. Because we got twice as much water. So this is actually a little faster, but it's the rate of oxygen is slower, so it's 1/2 of the speed of water being formed, and it's 1/2 of the rate of hydrogen peroxide being consumed. So if we got one molecule of H2O2 and we use up 2 of these a minute, we're going to get 1 of these a minute of O2 plus 2 of these a minute of H2O. That's how this is working. So this is what we mean by 1/2 of the concentration of O2 per time. And that's equal to a net positive 1/2 of the concentration of water. And this is, sorry, this is supposed to be 1 over time. And since we're losing peroxide, that's a negative 1/2 times the concentration of peroxide over time. So that's how it works. It works for any rate. But when we think of constants on rate laws, even though they're based on concentration, it's not based on the stoichiometry. It's actually based on how many react. So number of collisions. And let me rephrase that, number of atoms or molecules So it's a first order reaction, you need to have 1 atom. If it's 0 order, there's nothing, it just doesn't. Second order means 2 of them break out. And how we figure out the orders is experimentally. And the rate is equal to a rate constant times the concentration raised to the rate order. This is what NMM means. M&Ms are the order of the reaction. Rate order of the reaction. And the reaction order is just the sum of the exponents. And that's what we're looking at when we look at concentration. So we've got a couple of terms that we need to talk about. And we have initial rate, an instantaneous rate, and we've got average rate. The initial rate is the rate of being an experiment. That's what we usually work with. Instantaneous rate is great, but you need calculus to determine it, and it's a rate of reaction at a specific time, specific instant of time. And this is not used that much. But engineers like to use this when working out chemical reactions to bring up into factory specs. Now, average rate is average over time. Not that much at all. In this class, we're going to use initial rate, and that's the initial rate of an experiment. So we're going to look at how to work with kinetics problems and experimentally and find the rate or the reaction. Now the rate is going to be, the rate is equal to a constant times our reagents raised to the x power and O2 raised to the y power. So the rate is we're looking for something for the reagents. And when we do that, when we measure the rate, we're actually looking at the formation of NO2. This is the formation of NO2, and this is the initial rate. Now what's happening, we're changing our reagents. So in this, we're going to compare two experiments. So let's look at 1 and 2. I'm going to go back and forth here. So we're going to look at 1 and 2. So the rate of 1 is 0.048. The rate of 2 is 0.192. So what we're looking at is that the ratio of rate 1 to rate 2 to that is, and we're going to look at the concentration of 1 versus the concentration of 2, and we want to see what happens raised to some factor of x. And now, folks, to make it easy, let's put the highest first. So we're going to look at rate 2. The ratio of rate 2 to rate 1 is equal to the ratio of concentration of x2 over x1. And we want to know what that, and we're looking for this exponent. So rate 2 is 0.192, rate 1 is 0.048. That's equal to x2. Now let's go back to the day. What concentration are we changing? Between 1 and 2, oxygen is staying the same, but we're changing the initial concentration of NO, nitrous oxide, 0.015 to 0.03. So 0.30, 0.15, all right, so that's the ratio, and raised to some power, so they're equal to each other. So 0.192 divided by 0.048 gives me 4, and that's equal to 0.03 divided by 0.015 to 2 raised to the power. So what's x? X squared is equal to 4, so x is equal to 2. And that's how we work these problems out. So it's going to be second order with respect to NO, excuse me. Do the same thing with oxygen. And now we're going to come back and okay, which one we're going to do? We had two choices. We're going to do either 2 and 4 or 1 and 3. Let's look at 1 and 3. So 3 has the highest concentration, that's 0.096. 0.096 divided by 0.048. And the concentration, this is easy, 3.0 and 0.015. Raised to the power. We'll try to find out the power. This is going to be 2. And of course, this is 2 raised to the x. So x is equal to 1. So the rate order of oxygen is going to be first. So the rate equation is rate is equal to constant times NO2, I wish my pen would stop that, squared times NO, O2 to the first, and the rate order for the whole reaction is equal to 3. Rate order with respect to NO2 is 2, and with respect to oxygen, O2 is 1. And that's how we interpret that equation. Now, you also got to find concentration from reaction time. All these equations that we listed here come from calculus, and this also matches the graphing. Remember, if A, concentration of A versus time is a straight line, it's zero order. If it's log of A versus time, straight line, it's a first order. If it's a second order, it's 1 over A versus time, and that's going to be a first. That's a second order reaction. And no, with a second order reaction, we're only looking at one compound, not two. So just looking at one compound, you need two of them to react. And again, the actual equations are derived from calculus. And so the example is that we have a first order reaction, so we're looking at this reaction here, the logarithm. We want to know how long will it take, how much hydrogen peroxide we'll have after 4 hours. This is in seconds, so we've got to change the hours to seconds. So that's 4 times 60 times 60. That's going to be 14,400 seconds. Here's our rate constant. So the equation we're going to use is natural log of concentration of H2O2 at time t over the concentration initial, what I call time 0. That's equal to minus k and the time it takes to do this. So let's go back and look. Initial concentration is 0.3 molar. So H2O2 at 0 is 0.3. We want to know what the concentration is at whatever time. Time for us is going to be 14,400 seconds. That's what we got here. That's 4 hours. And remember, K is equal to 1.8 times 10 to the minus fifth. Now, let's go ahead and plug all this in. Now, to get rid of this, raise both sides by a factor of E. So you have concentration of H2O2 times time at time t versus 0.3. That's equal to E raised to the minus k times time. I raised both sides to e to the power, and we got these two. So the concentration of H2O2 at 4 hours is equal to 0.3 times e to the minus k, which is this number in scientific notation, times time, which is 14,400, and we should get this value. Now, I want to point out with this, I would do the exponent first, so take 14,400 times 1.8 raised to the -5th, and then multiply it by -1 to change that into to make it negative. So we have 0.3 times e to the minus 0.2592. And that's my concentration of H2O2 times time. So I take E raised to that value, which is 0.77. And so my change times 0.3. And the concentration is 0.232 molar. And that is how you work those problems out. And I'm running out of time, so we'll finish this later. Have a good day, folks.